Today, we will quickly recapitulate some of the crucial, important ideas that we discussed last time, and then we will follow it up by discussing the case of a stationary quasi-monochromatic field with a Gaussian spectrum, and see how the bandwidth and the coherence time are defined for this particular case. And then, if time permits, we will start spatial coherence. Otherwise, we will wrap up our discussion on temporal coherence today, and next time we meet, we will start spatial coherence. So, just to recapitulate some of the important things that we discussed last time. So, if we consider an interferometer, the intensity at the output is written as so this is the intensity of the output of the interferometer. And this is the degree of temporal coherence, this gamma. And this tells us that if the fields are completely incoherent at different instants of time, there won't be any interference. So in order to observe interference, in order to observe the fringes, there should be some kind of coherence between the fields at different instants. Higher the degree of temporal coherence, better will be the interference fringes. Now, in interferometry, there is a very useful quantity that we define and that we measure called the visibility, which is given by this formula. It is I max minus I min. So visibility varies between 0 and 1. 1 corresponds to the best contrast, and 0 corresponds to no interference at all. And for partial coherence, V will be anywhere between 0 and 1. So for this particular case, V is given by so you can see that visibility essentially depends on the degree of coherence. There's a direct relationship between the visibility and the degree of coherence. So experimentally, from an experimental standpoint, the visibility basically reveals how strong or how poor the temporal coherence is between the fields at different points, at different instants of time. And in this context, just to quickly recapitulate,
basically it takes I max and I mean with respect to these phases, right?
Exactly. So this one. So experimentally, this K is something that we vary by changing the path length, adjusting the mirror, so on and so forth. So another important theorem, a pair of expressions that you need to keep in mind when we study optical coherence is the generalized Wiener-Khinchin theorem. So So this is one of those things that needs to be boxed. This relates cross correlation function to cross spectral density. So we are simply summarizing the important concept that we discussed in temporal coherence. And this is the cross spectral density function. So once we know the cross spectral density, it's straightforward to calculate the cross correlation function, because these two form a Fourier transform pairs. So the final point in this exercise of recapitulation is the cross-spectral density of a Gaussian shell model source. So this is the most realistic source that we have, that we use in the study of optical coherence. And this is a partially coherent source. Unfortunately, we won't have time to go through this particular model in detail. But if you're interested to know more about the Gaussian shell model source, I would encourage you to read Wolf's book. There's a thin book by Wolf that's called Introduction to Coherence and Polarization of Light. And if you want to go into greater detail, please refer to the book by Mandel and Wolf. That the title of that book is Optical Coherence and Quantum Optics, things published by the Cambridge University Press. So that has a lot of details. But for the purpose of our discussion, we would simply yeah.
Professor Simon has worked on these Gaussian cell models.
Yes, he has. Professor Simon has worked, and in fact, Professor Simon and Professor Mukunda invented a particular kind of beam. It's a variation of this one called the twisted Gaussian shell model beam. This was invented in the mid-90s. They published two beautiful papers in JOSA B or JOSA A, Journal of Optical Society of America. And recently, interestingly, twisted Gaussian shell model source is becoming popular because Walborn published a few papers a few years back in 2021, where he showed that if this pump is, instead of being a Gaussian pump, if it is a twisted Gaussian shell model pump, then interestingly, the degree of entanglement, spatial entanglement between the twin photons increases with the increase in the incoherence of the pump. So typically for a Gaussian pump, more incoherent the pump is, the less entangled the photons will be. So the degree of entanglement goes down with the incoherence of the pump. Whereas for the twisted Gaussian shell model pump that was invented as a theoretical concept by Professor Simon and Professor Mukunda, interestingly, the degree of entanglement increases with the incoherence of the pump to a certain range. So that's, yeah, so there is an IMSC IISc connection for the Gaussian cell model source.
The paper of Walborn is recent for that.
2021 Physical Review Letters. I can send you the papers. And also he published a second one in this AWS Quantum.
This is what, a experimental paper?
Both theory and experiment. In fact, in the Physical Review Letters paper, Professor Walborn has acknowledged Professor Simon for insightful discussions, for helpful discussions. So
Walborn is a Brazilian. Right?
it's a Brazilian. Interestingly, Walborn is an American. He was David Griffiths' student during his undergrad days. The same Griffiths who wrote a book on who has this book on electrodynamics and quantum mechanics. So he is an American, born American, but he fell in love with South America. That he moved to Brazil for his PhD. He worked with Moncan, Carlos Moncan, and then he fell in love with South America, and he chose to stay there. So he was in Brazil for many years, and now he has moved to Chile. He has his own lab in Chile.
Okay. Because I know Simon visited Brazil some time back.
It's during that visit that I'm pretty sure Walborn had some discussions with him in 2021 or 2020, around that time, maybe before the pandemic. Before that, yes. So it's in that context. So since you brought this one of the problems that when I read Walborn's paper was, does this property of twisted Gaussian shell model hold good only for continuous variable entanglement, or can one also explore this for polarization entanglement and OM entanglement? Like if you make the pump incoherent, will the degree of entanglement in the other degrees of freedom also go up with the incoherence of pump? That has not been explored. That is still an open problem.
Yeah, so there you will have to introduce the notion of coherence in the case of discrete variable.
Yes, so that is correct. So how that can be, yes, how to introduce coherence. But that can be done in a sense. Emil Wolf has worked out a very unified has worked out a unified theory of coherence and polarization in terms of, in classical optics, where in terms of correlation functions you can introduce polarization in terms of correlation functions. Then it has to be extended. So if it can be done for polarization, then one should be able to do it for OAM as well.
Yes.
In terms of angular correlation, so on and so forth. But one has to understand the notion of this twisted Gaussian shell model pump and the physical meanings in some detail. Yeah. So so this is what this is how we write down the cross-spectral density of a Gaussian shell model source. It's a product of two Gaussians, and this omega, this is the frequency on which the spatial coherence width or the beam radius of the source depends. This omega determines radius, and this omega c, this determines the spatial coherence length. So if it determines the spatial coherence length, it's this quantity omega c that will also influence the coherence time, tau c. So the final point before we move on to quasi-monochromatic Gaussian source. The two extreme cases, the case of no correlation and perfect correlation, basically are the limiting forms of the Gaussian cell model source. So take this limit, omega c going to 0. In that case, this becomes a delta function, the second Gaussian. So the first Gaussian simplifies to omega 1 becomes omega 2. Now, this form is something that we have seen before. This is the spectral density times a delta function, and this corresponds to the case of no correlation. And that is because of this delta function. So the presence of this delta function tells us that the cross-spectral density is non-zero only when omega 1 equals omega 2. When omega 1 is not equal to omega 2, the cross-spectral density vanishes, which means there is no correlation between the spectral components of the field, the different spectral components of the field. The second case, limiting case, is omega c tending to infinity. In this case, this becomes 1. In the limit omega c approaching infinity, the second Gaussian becomes 1. So basically, we are left with just the first term in the Gaussian shell model source. So which means this can be written as the product of two terms, a Gaussian involving omega 1 alone times a Gaussian involving omega 2 alone. So this is the case of perfect correlation. Right. Okay, so any question from the online participants?
No questions.
Okay, so these are the important results in the study of temporal coherence. So now we will move on to the case of a stationary quasi-monochromatic field with a Gaussian spectrum.
Just a minute.
Yeah.
Of course, this is not into this. So when they have done this twisted beam, what exactly they have taken?
So basically, what happens is, along with this one, there will also be so in the case of Walborn, he considered a pump in spatial degrees of freedom, x and p. So there is this twist phase that has to be introduced between the x quadrature and p quadrature. Okay, and it is that twist phase which basically changes everything. So that comes up here, and when one derives the covariance matrix and looks at the degree of entanglement, it turns out that by increasing the incoherence of the pump.
Saying that in the twisted Gaussian shell model.
Oh, here.
Here it should be some change, right?
Yeah, so there will be this another term, a phase factor that comes up, which is the mathematically it's the wedge product between x and p, I times x product wedge product p. So this phase factor comes up in the cross-spectral density.
I times xp minus px.
Exactly, I times xp minus px. That comes up in the expression of the cross-spectral density. So that becomes a twisted Gaussian shell model source.
So it is this phase that takes that.
Yes, it is that phase that basically changes the behavior of the system.
And I mean, how does one create such a beam?
So that is always this twisted. It's not that easy to generate these beams. So I have to think Walborn, he basically, I don't remember the details. They found a way to generate these beams in the lab. So maybe I'll look into the references and uh, uh, I'll share the references and let you know. I'll have to once again read them up. But these beams have been produced. They're still being investigated, but they're not as common as the Gaussian.
Because what I'm asking is, this entanglement they have seen in which degrees of freedom?
Spatial degrees,
Spatial.
x and p, x and k, basically position momentum.
Okay. That is they have seen, right?
Yes.
So then these, generally the continuous variable case, when we talk about entanglement, generally some kind of non-classicality is required in the input field.
Yes.
I mean, unless you are using some non-linear optical gadgets.
Yes. So how? Okay. So in their case, the way they generate the entangled photons is through SPDC.
Okay.
So the crystal is the conventional nonlinear Chi2 crystal.
Yeah.
The pump is a TGSM, twisted Gaussian shell model pump.
Okay.
So, but the question is, I have to once again look into literature to find out how that twisted Gaussian shell model pump is produced, because I'm pretty sure.
The beam that is coming out, this is an entangled linear because it is coming out of SPDC.
Yes, it's because the pump. So this is something that Monken showed, that the angular spectrum of the pump is always, the properties of the pump are transferred to the entangled photons through SPDC. So because of that, the twist phase, whatever novel feature the pump has, that's transferred to the entangled photons.
Okay.
But the production of entangled photons is through SPDC, conventional SPDC.
Because conventional SPDC, if you look at, I mean, you basically use some standard pump,
That is true.
It is a Gaussian beam or whatever.
That is true.
So that, of course, the amount of entanglement, as far as I know, there it should not depend upon the pump intensity.
No, yeah, it doesn't depend on the intensity. And as such, for an entangled pair, the intensity has to be weak anyway to suppress multiphoton emission.
Yeah, that is. But the question is that, so this is a spatial character of your input.
Exactly.
The pump. So by changing the spatial character, you can change this entanglement.
Yes, the degree of entanglement.
That's what I'm saying. So that is bit interesting. Okay.
From a practical standpoint, that generated some interest because making the pump more and more coherent is a challenge. One has to be.
Yeah, right.
So if you have a source, a pump where incoherence aids the degree of entanglement, then it's a valuable resource from a practical standpoint.
Incoherent source?
Yes.
Produce more entangled states.
Exactly. But I'll have to read how they're actually producing the twisted Gaussian shell model source.
But in terms of the success rate, that like in SPDC, standard SPDC, generally we say that this is of the order of 1 by 10 to the power 6.
Yes, I don't think this gives any better result in terms of efficiency.
Okay.
Because it's still the same. As far as the medium is concerned, it's just a pump that is illuminating and
yeah, but the good thing is that even if you use incoherent pump, still it can produce more entangles.
exactly.
That is interesting. Okay.
So the question is the same Gaussian pump, the conventional Gaussian pump has been used to study entanglement in various degrees of freedom, like
Yeah,
spatial degrees, OAM, polarization. So the question is, can we still exploit this twisted Gaussian shell model pump and investigate entanglement in other degrees of freedom?
Yeah, that is true. In other degrees of freedom, whether one can do it.
Particularly OAM, because of its relevance in various quantum information protocol. More than 2 degrees of freedom.
Yeah, so in some sense, the question is this: it is important to look at this. How do they introduce this twisting thing?
Yes.
Because it is ultimately a classical effect.
That is true. It's a classical effect, and that's how Professor Simon and Professor Mukunda, when they introduced this one, they introduced within the realm of classical optics.
Yes. So, introducing a classical effect like this fields, and that is enhancing your entanglement.
Yes.
So this is something very interesting.
A few years back, Walburn gave an online talk in IIT Kanpur, as Anand Kumar Jha has his own YouTube channel, this Coherence and Quantum Entanglement group. So he gave a talk. I can also send you the link to that talk, because he's the only one who's investigating this kind of a problem in the realm of within the realm of quantum optics.
Yeah, we can have discussion.
Yes, we can. I tried to read the paper by Simon and Mukunda. Of course, it was too formal because they invoked a lot of group theoretic ideas. So I got the gist of that paper and tried to then look into Walburn's paper to get, because they mathematically reasoned out how the various formal mathematical group theoretic arguments uh, explain the properties of the twisted Gaussian shell model pump. And I have not had formal training in group theory, but I can send you the papers. This one I wanted to, this is something it has been in my mind for at least 2 years, but I never got a chance to discuss some of these things with anybody. So want some input about the twisted Gaussian shell model.
No, I knew that Simon has worked on this twisted Gaussian shell model, but that it has been used here like this.
In a sense, Walburn resurrected that problem. It was otherwise not, the paper is well cited, but it was quite forgotten in recent times. And Walburn, again, he has regenerated the interest in TGSM. So now we will now we'll consider the case of a quasi-monochromatic Gaussian source. So we are going to consider a stationary quasi-monochromatic Gaussian spectrum. Just to recall, let us recall that if the field is stationary, this is how we write down the cross-spectral density and this two-time correlation essentially depends only on the time difference. And the intensities are independent of time. So in this case, this D stands for detector. The intensity of light measured at a detector becomes now this gamma of tau is the correlation function. Now, what is a quasi-monochromatic spectrum? So we call a spectrum quasi-monochromatic if the bandwidth, so basically you plot S of omega. Let's say you have something like this. This is the central frequency. This is the bandwidth. Now, if the bandwidth of the spectrum is much smaller than the central frequency, then we call such a spectrum quasi-monochromatic. Now, so basically the spectrum depends on omega naught, primarily on omega naught, and the spread around omega naught is extremely small. So I suppose you can see the board, right? I think something popped up on the screen. Can you see the board clearly?
Yes, sir, we can see the board.
Okay.
Excellent, sir.
Yes, please.
For this quasi-monochromatic source, you told delta omega is very much less than central frequency.
Yes, then omega naught, yes.
Yes. Then in case of monochromatic?
So monochromatic means it's the most ideal case. It just depends on a unique frequency, single frequency.
Okay.
Delta omega should be 0.
Yeah, delta omega should be 0 for the case of a purely monochromatic field.
Okay. So that would be the ideal scenario.
That's the ideal scenario. So in all the textbook examples that you would have seen, like a e power I k x minus omega t, that kind of an example. So you assume that it's a perfectly monochromatic field where it depends uniquely on a particular frequency.
Okay.
But here we nevertheless still write down everything in the multimode framework in terms of the spectral components. But delta omega is much smaller than omega naught.
But in reality, no field can be monochromatic.
Yes, no field is monochromatic in reality. So this is an approximation. In fact, in the lab, when you do an experiment, this is the best case scenario for you. So like lasers are examples of quasi-monochromatic sources, a well-tuned laser. So recall that this is what it is, omega of gamma of tau. This follows from the Wiener-Khinchin theorem. Yes.
Maybe slightly different.
Yes.
So when you look at the SPDs, you have this laser pump, right?
Yes.
So which is quasi-monochromatic.
Yes.
So now if I want to look at So ideally, the correlation, let's say in the frequency of this Heidler signal.
Yes.
It is it is highest correlation if it is a monochromatic light. Is that the case?
The correlation is you have the best correlation again in, let us say, in momentum, you will have the best correlation if the pump waist is larger.
Pump waist is larger. The delta omega is larger.
So not so much about this, not delta omega, the pump waist. So the monochromaticity of the laser doesn't influence the spatial correlations.
Okay. No, I'm talking about the frequency correlation.
So frequency correlation
in the signal and Heidler.
So the time frequency correlation, probably that will so omega s and omega p. Yes, in that case, if it is the more, because omega sub p should be omega sub s plus omega sub I. So if you get the strongest correlation if omega sub p, the frequency of the pump, doesn't vary appreciably. So in that case, you're right. In terms of this one, yes.
There you get better correlation if you take, the basically monochromatic.
Monochromatic, in a sense, the laser has to be tuned in frequency. It should be a fine-tuned source before passing through the crystal. So in this case, let us just substitute for omega to be omega sub 0 plus omega prime. So in this case, you will get so it just so that follows from the Wiener-Khinchin theorem.
Because it is a frequency, it has to be generally positive.
Yes, but then it dies down rapidly, that harmlessly you can just extend.
That is true, that you can do. Yes.
But otherwise, of course, there are problems. No, you're right. There are problems where you will have to introduce cutoffs explicitly, like particularly when we study the propagation of pulses, photon pulses through an optical medium. To avoid divergence in the theory, we will have to introduce cutoffs in frequency to account for the finite bandwidth. So we are not doing anything different here. So this can be written as so this just comes out as a phase factor, the central frequency. Now, let us consider a particular case where the cross-spectral density is a Gaussian. This is normalized. Now, delta omega is the width of the spectral density function. Or you can also, this is also known as the frequency bandwidth, or another word is spectral bandwidth. So you will see one of these terms or one or more of these terms being used in literature. Sometimes they would be used interchangeably. So they mean the same thing. Okay. Now, once we know S of omega, using this formula, we can calculate gamma of tau. And if we do that, we get this one. And then where tau c is defined. So the coherence time is the inverse of the frequency bandwidth or the spectral bandwidth. So in other words, once you know delta omega, you know tau c. But please note that this is not always the case. This trivial relationship holds good only for a Gaussian spectrum, because Gaussian spectrums are single peaked. But if you happen to have a source that produces multiple peaks, it's not that easy to define the spectral bandwidth or coherence time. Okay, but in this case, that's why so far you have not made any formal attempt to define the coherence time and spectral bandwidth, because if your spectrum has multiple peaks and multiple peaks of different widths and different heights, it's not straightforward to define the notion of coherence time and spectral bandwidth. So we are considering a simple case where the spectrum has only one peak. And if it's a Gaussian, the coherence time and the spectral bandwidth are given by the standard deviation of the curve. Okay. So once we have this one, we can define gamma of t. Now gamma of 0 is 1, because when you set tau to be 0, this becomes the right hand side becomes 1. So basically, and the modulus is given by so if you want to measure for this particular source, if you want to measure the intensity at the output of your interferometer, and gamma of 0 is 1 in this case. So intensity is 1. So mod k1 square So you have this interference term, but it's also modulated by this Gaussian. So which means you won't see the fringes forever. So they will die out over some length. Okay. So that's what it is. Since we have a seminar,
Dies out at okay, yeah, so that is true. At some length it will die because of this Gaussian.
exactly. In a sense, yeah, so you can see this interference term is modulated by this.
Yeah, that is true. But the question is that Intensity, this is intensity at the output.
That is correct. Intensity at the output. So
intensity at the output, if it dies down,
so
it dies off, it will be output.
yes.
So intensity is some sort of energy. So basically, energy is somehow dissipating. So where is it going? I mean, what is the reason behind this?
It's once
I mean, you have taken the bandwidth is something like Gaussian one.
that is correct. That is correct. That is correct.
It is dying down over time, right? Over tau.
Yes, but tau can also be related. So if the tau can be related to delta x, because if you just consider a simple anyway, I was trying to work out an example, but just catch the idea here. So if basically, yeah, a simple thing. So let us say it's xt. Let us say that T2 and tau is T2 minus T1. And for this particular spectrum that we considered here, one can actually do the calculation and show that, and let us say this is R, distance between the slits and the screen. This is what it is. So if no
Oh, now you have increased, either you increase the, so if you increase these, the separation between the two slits.
Yes, if you have to increase the separation between, well, if you increase the separation between the two slits, so that then you'll increase the delay. That is correct. That is correct.
Yeah,
but that would not change the coherence.
Yeah, that is true. It will not change the, but if I let's say take the coherence time tau c to be very, very large.
Yes. So if tau c has to be very large, then yes, this has to be extremely narrow.
Yeah.
Delta omega has to be extremely small. So in fact, if this is put into this expression here, then you would get something like I of x. So let us say this is x. This will be so this tells us how the intensity is going to vary as a function of x. The farther we move from this origin, the intensity will decrease. And it just tells us that, which means we are going beyond the coherence length.
Yeah.
So basically, we are measuring the intensity beyond the coherence length. That's why there is no interference. I mean, it dies. Well, actually, I've been careful. So what dies down is what dies down is the fringe, not there is. You will still detect the light.
Yes, you will. So basically, the fringe will die.
The fringe will die. So I should have been careful. So it's not as if the intensity itself vanishes, the source vanishes. It is just that the fringes will disappear.
Yeah, the fringe will disappear because this cosine term is with this.
Yes.
If this exponential is too small,
Yes.
then of course fringe will disappear.
So we'll just the detector will just capture the light.
Yes.
And there'll be
there
won't be any fringe.
Yeah, that has to be the case. Otherwise, there is no energy exchange. Nothing.
Exactly. So the energy doesn't. Of course, in this case, there's no dissipation. Yes. So which means the detector will still capture light, but no interference pattern. So anyway, this example for those attending online, we'll work out this example next time, and then move on to spatial coherence. Okay, so that will so this basically wraps up our discussion on temporal coherence, right? So yeah, next week I'll be traveling for a conference. So we'll meet on 21st of October.
21st.
Yeah. So I'm returning on Thursday. So we'll meet on 21st, the Tuesday after Diwali. So yeah, those online. So we'll meet on 21st of October.
Okay, sir.
So by the way, I don't know whether so you're part of the quantum information at IMSC group, or do you get emails? Okay. Can you please?
Sanam gets the email. He only forwards us.
Okay. So I believe Sanam is also part of the WhatsApp group, I believe. Okay. So anyway, I will post send a reminder on 21st morning saying that we'll meet in the afternoon. So hopefully you should get the update from Sanam. But anyway, we'll meet on 21st October.
Okay, sir.
Yeah, thank you so much. Thank you.
Thank you, sir.
Yeah, I'll forward these two papers by Walbun to you.
Yeah.